Welcome back to Statistical Reasoning. We are proceeding in Chapter 4, and we're going to move on to the addition rule and the multiplication rule. So the addition rule that we need to think about is whenever somebody wants to know what's the probability of something or something else occurring, then we have to add those probabilities together to find out what that actually is. And the multiplication rule, if somebody wants to know what's the probability of A and B occurring, so we see the word and, that we are actually going to multiply the probabilities together. A compound event is when we actually combine more than one event. So notation-wise, we're going to use probability of A or B. Now when that happens, don't forget it's that event A occurs or event B occurs or they both occur. So in this case we have to make sure we don't forget that it does include them both occurring. Now we're going to do an example here pretty quickly about how this works, and one of the ways is just to think about it in common sense terms where you just actually count them up and make them happen. Or there is a formal rule. So probability of A or B occurring is the probability of A occurring, so the first event, plus the probability of the second event occurring, minus the probability of them both occurring. And the idea here is we have to make sure that we don't accidentally double count any of the options. Another term that we need to know is disjoint or mutually exclusive, and in this case we're talking about things we have to make sure that they can't both occur at the same time. Here are some examples. If we go to a clinic and we randomly choose somebody out of the clinic, event A is that that person is a male. Event B is that that person is a female. You can't pick a person who's both a male and a female, so they are disjoint events. Not disjoint is when they can both occur at the same time, choosing somebody who's in a stats class, choosing somebody who's a female. Well, you can be a female in a stats class, so these are not disjoint events. One thing we talked about in the last section was the idea of being complementary or a complement, and a complement was the opposite of what we were looking for. If the probability of what we're looking for and the probability of what we're not looking for, that should include all of the options in whatever you're dealing with. So together their probability should be a 1 or 100%. Formally it can be written in this way: probability of the event plus probability of the event not happening is 1. Or we can do a little algebra. So the probability of it not occurring is 1 minus the probability of it occurring. The probability of it occurring is 1 minus the probability of it not occurring. So here we have a sleepwalking instance, and it says the probability of a random person sleepwalking is 0.292. If this person is randomly selected, what would be the probability of getting somebody who has not sleepwalked? So not is the complement, and as the previous selection said, probability of it not occurring is 1 minus the probability of it occurring. So we can go 1 minus 0.292. So we're going to get 0.708. The multiplication rule, so its notation is probability of A and B occurring. This one, when we read the bottom one, it says probability of B given that A is occurring, and so this one's a little bit different because we're knowing a little bit about the information prior to determining its probability. We can do it intuitively, or we can do it with a formula. Items are meant to be independent or dependent depending on if they are affecting each other. So if I have two events and the first event affects the second event, they are not independent, so they are dependent. If they have no effect on each other, then they are independent. So here's an example where we have 50 subjects who were tested for drugs. 45 of them had positive results and 5 had negative test results. If two of these subjects are randomly selected with replacement, find the probability that the first person selected has a positive test result and the second person selected has a negative test result. So we'll start by doing A first. So let's just think of this one person at a time. So we know that from the previous slide, and we're looking at a positive result first. So from the previous slide, we have that 45 people had a positive result. So 45 occurred, and there were a total of 50. So as we talked about in the first section, 45 having the positive and 50 total is the probability. Now when we talk about not replacement, that means that individual that you chose goes back into the pot, and so their name is still in there and I could choose them again. So now I need to think about what's the probability of the second person having a negative test result. Well, in this case, 5 had negative test results, but since everybody's back in the pot, it still would have 50 people in the option. So let's go ahead and reduce this. 45 out of 50 are both divisible by 5, so it becomes 9/10. 5 out of 50 are both divisible by 5, so it becomes 1/10. So the probability of choosing first a person with a positive result and then a person with a negative result is 9 out of 100, or 0.09, or 9% of the time we would be able to do that. Now on B, they're changing it up a little bit. It says repeat it, but assume this time we are not replacing it. So once somebody has been chosen, they can't be chosen again. So in the first case, we still have 45 out of 50. That part doesn't change because we're still looking for a positive result. We're still looking for the first person being a negative, which is 5. The difference is I no longer have 50 people in the pot to choose from. Since I kept the one out, I'm now down to 49 people in the pot. Still going to reduce the 45 out of 50 to 9/10. 5 49ths doesn't reduce, so I'm going to leave that. Still multiplication in the middle. I am going to do some simplifying here before I keep going. 5 goes into 5 once and into 10 twice. I just don't want to multiply larger numbers. 9 times 1 is 9. 2 times 49 is 98. So it's 9 out of 98. So if I want to change that, that is approximately 0.092, which is approximately 9.2% of the time. So the probability went up just a tiny bit by taking out the idea of replacement. Since sampling with replacement, those are independent events because who you choose in the second time has no effect on, say that again, who you chose in the first one has no effect on who you chose on the second one because everybody's going back into the pot. Because you took somebody out of the pot and kept them out of the pot, that does have an effect on who the next person is, so those events are dependent if you don't replace them. So how that affects what's going on, if you have less than 5% of the sample that you are testing, then you can go ahead and treat them as independent events even though they are dependent because it has such a minimal effect. So if we are choosing 3 adults randomly selected without replacement from 247,436,830 adults, we are assuming that 10% of them do drugs. Find the probability that the 3 selected all use drugs. So without replacement means we're keeping the person out, and so it'd be a little bit hard to do this one with just the fact of the 10%. So let's check and see if we can use the rule of 5%. So back here we said if our sample size is no more than 5% of the population. So let's figure out what is 5% of 247,436,830. Typing that into my calculator. So it's still a nice large number, 1,2,3,7,1,8,4,1.5. So it's still 12 million. So if we have anywhere less than 12 million in our sample, we are still under the 5%. Well, we're not even close, we're doing 3. So we can actually treat this as if they were independent, which means that we're going to just use them as is. So I'm choosing 3 people. Each one of them has a 10% chance of using drugs. So it's going to be 10%, and I'm going to change it to a decimal, times 10% times 10%. Now you might ask yourself, why am I multiplying? I'm multiplying because I'm doing all of these adults. I need the probability of this person doing drugs, and the second person doing drugs, and the third person doing drugs. And in the and situations, we are multiplying. So it's 0.1 times 0.1 times 0.1. So it's 0.001. Oops, what happened there? So that's a 0.1% chance that I would choose 3 people that do drugs. So we have this thing called the principle of redundancy, which is used to increase the reliability of systems. So they give us the example here of our eyes. If one eye went down and something happened to it, we still have a second eye. Yeah, we maybe can't see quite as well, but at least we have a backup plan. And so anytime we have, and I know in electronics a lot of times they have that happen, so if one system fails, there's a backup system that will take over. You know, our hospitals always have this idea of redundancy going on. If the power goes down to take care of their patients, they have the backup generator. So they have the principle of redundancy in effect as well. Here we have an example where we have a modern aircraft, and so if something fails in one of their systems, like their engine, well, they could crash. So they want to make sure that in our current airlines, with the technology that we have, that if something happens to an engine, it still could stay up in the air. Whereas our older engines that were a single engine props, that wouldn't happen. So the example they're giving us here is an Airbus 310, which is a twin engine airline, and it says they have 3 independent hydraulic systems. So if one system fails, they can still control what's going on. So for this example, we will assume that the typical flight, the probability of a hydraulic system failure is 0.002. So A, if the Airbus 310 were to have one hydraulic system, what is the probability that the hydraulic flight Airbus would work for a flight? So they only have a single one, they're saying, and if it's 0.002 that it would fail, and they want to know the probability that it would work, that is actually the complement. So we would have to do the probability of it working would actually be 1 minus 0.002. So it has a 0.998 or a 99.8% chance of working. That's if it was in a single system. Now, this actually has a 3 independent hydraulic system set up. So what is the probability that on a typical flight, control can be maintained with a working hydraulic system? So when we look at this one, we have to look at it a little bit differently, because if we think about it, the system would still work if 1 failed and 2 were working. If 2 failed and 1 was working, it would still work. Or if all 3 were working, it would still work. The only way that it wouldn't work, if the plane would go down, is if all 3 failed. And so when I'm trying to figure out this probability, really I would need to find out the probability of 1 failing and 2 working, and 2 failing and 1 working, and 3 working, and combine all of those. It actually would be easier to do the complement in this case. Let's figure out what's the probability of all 3 failing, and then find the rest of them, instead of adding the 3 different ones up. So let's talk about the probability of them all failing. It said the probability of 1 failing is 0.002. So if the probability of the first one failing is 0.002, the second one failing is 0.002, the third one failing is 0.002. So 0.002 to the third 1, 2, 3, 4, 5, 6, 7, 8. So it's 0.000000008. So that's the probability of them failing. Well, we're actually looking for the probability that this is still going to stay in the air, so it's going to be 1 minus that. So that's going to be 0.99999, 1, 2, 3, 4, 5, 6, 7, 2. So we can feel pretty good riding on an Airbus 310 because the probability of it staying in the air is almost 100%. So just as a recap, if you see the word or, we know that we are adding. If we see the word and, we know that we are multiplying. Thank you and that actually is going to end our chapter. We're only going to do the first 2 sections. The rest of it you can learn about if you take a higher level statistics class. And so make sure you work on your assignments and let me know if you have any questions.